Now, the first session of this beautiful day is coming to an end, but no need to worry, this is just a beginning. To extend and express our vote of thanks, I invite Professor Robert Joe, Head of Department of Nanoscience and Technology and Nanotechnology, University of Kerala, Trivandrum.
Good morning. Respected Professor PBR Chaudhary, Senior Executive Director, President, Material Research Society, Singapore. Professor KVR Murthy, President, Luminance Society of India. Professor Gopakumar, Controller of Examination, University of Kerala. Dr. Anjana, Head of the Department of Physics, All Science College, Trivandrum, and other faculty members from different colleges, universities, research college, and my dear students. I am very happy this morning to listen an enlightening talk by Professor B.V.R. Chaudhary. So, this is actually a challenge for the young physicists who are attended here for this seminar. So this is your responsibility for developing a materials that's sustainable for the society. So all the young physicists, students, you take this as challenge to develop the material which are sustainable to society. So he has given an excellent talk. So on behalf of the organizing committee and my own behalf, I extend my sincere thanks to Professor B.V.R. Chaudhary for this. Next, Professor KVR Murthy. So he has also given an excellent talk related to the luminous material. So this is also an enlightening talk. So I thank on behalf of the organizing committee and my own behalf, I extend my sincere thanks to Professor KVR Murthy for this seminar. And next, the organizers of this meeting, is the coordinator, Professor Gopakumar, Controller Examination. So he has taken a pain to arranging the conference in an excellent way. I thank this time to the opportunity to thank Professor Gopakumar for this wonderful arrangement. And the convener of this conference, Dr. Anjana. So even though she is from Trivandrum, she has all the arrangements. It is quite far away from this place. So all the arrangements in a wonderful way. So I also thank Dr. Anjana for this wonderful arrangement. And so, even though we are in Trivandrum, so the other co-conveners, the head of the department of SD College and nearby places, and the other Dr. Ragesh, I have seen that he took a lot of pain for since the meeting is a hybrid mode, so he has arranged in an excellent way. So on behalf of the organizing committee, I extend my sincere thanks to Professor Dr. Ragesh and other head of the department, other conveners for this excellent arrangement. And all the other faculty members from other different states and other colleges, I also extend my thanks to the on behalf of the organizing committee and all the research scholars and the students. I also thank you very much. Thank you so much. Thank you.
I request all the people, those who are at the registration desk, sir, please kindly join. The desk will be there till evening 5 p.m. or 6 p.m. So good evening to all of you. This is Professor Dinkar from National Institute of Technology, Warangal, a close friend of Professor Murthy. Before reading the small resume of Professor Srikanta, let me share 2-3 points. There are 2 good days in my life and there is 1 bad day apart from the 2 good days. One good day is 26th August, that is the birthday of my son. And another good day is 25th October, birthday of my daughter. And the most important bad day is 11th February, that is the marriage day of my. Generally, I used to attend several conferences, maybe 100 or 150 so far, only to escape, the sun effect or something. So when you are going to the summer, there will be heat effect, sun effect. To escape my wife effect, I am roaming all the places for the last several years. Sometimes my wife tries to come. I will make all the arrangements, and at the end of the day, I will say the organizer got heart attack and died. I am going to visit his cremation and other things. I will attend the one. So today also I am speaking so much happily because I am alone. But I must appreciate Professor Janalagadda. The bonding between them, it may be coordinate bond or covalent bond or anything. I have seen number of times, Sir is not moving anywhere without his wife. The required energy, patience, everything is getting from Sir. Now, Sir wife is also here. Sir, really I am appreciating for you. And Sir is having a vast experience. So if at all I am giving, reading the biodata of the Sir, it takes one session of 30 to 40 minutes. So briefly, 2 minutes I will read. Professor Srikanta B. Jonalagadda, Senior Professor of Chemistry, and as I told by my friend Murthy, is from South Africa, sir. Honors Fellow 2012, University of Natal, Fellow 2012, South African Chemical Institute, Fellow 2015, African Academy of Sciences, Fellow 2018, AP Academy of Sciences. Experience Senior Professor of Chemistry at Durban, Head of School of Chemistry, University of Zimbabwe. Several things are there. Sir research interest materials and applied catalysis, green chemistry, value added conversions, water chemistry, environmental analytical chemistry. H index is 47. Citations are greater than 10,000. I think all of you know the citations. And it gives me immense happiness and pleasure. My citation is only 50, but I am able to read a gentleman's biodata whose citation is greater than 10,000. So 26 PhD is completed and around 50 to 100 MSc prize completed. Total publications in the refrigerator around 500, and recently in the 2020, 21, 22 around 50 to 60 publications. He completed totally 200 international conferences, and in India around 50 conferences completed. So this is a small resume or a brief biodata one. Before inviting Professor Jonalagadda sir, with the kind permission of my friend Professor Murthy, yesterday for the last 1 week I am totally busy with marriage of my brother's daughter. From Friday to yesterday I am having lot of fever, cold, everything. But all the way I came to say greetings, birthday greetings to one birthday boy, and I procured a new shirt. You can see this one, Van Hussein, 5,000 rupees cost. You may ask, you have to give shirt to birthday boy, but the birthday boy loves me to wear the one. So is none other than, the person is none other than our Murthy sir. It is a happy birthday to Professor Murthy. There are two relations in our day-to-day life. One is human relations, another one is object or money relation. Myself and Murthy are least worried about the money relations or object relation. If 2 NP is less, don't worry. But human relations are decreased by 1%, we won't accept. We are maintaining those relations for the last several decades, praying the God and praying the God's country Kerala to give enough power, boost to us to maintain the relation in the future. Thank you. Sorry to say a few words, sir, but the time given is 30 minutes because it is already 12:30, and after 2 o'clock, whatever we are telling, people are not in a mind to listen. So 3 speakers are there. I am giving 30 minutes. So with these few introductory lines, I invite wholeheartedly, honorably, Professor Srikanta Jonalagadda to come and occupy the dais and start the lecture. Thank you. Thank you.
Everybody in South Africa, they say good day when we are not sure whether it is lunch time or the breakfast time. When we are in between area, that's why good day. Coming from South Africa, of course, from my accent, I'm from India, but now I'm South African. For the last 25 years I lived there. My university where I come from is one of the top 3 research universities in the country. We have got about 17 universities. Everybody will talk about the university. I talk about KwaZulu-Natal. KwaZulu-Natal means, Kwa means, place of Zulus. That province is of Zulus, that's why it's called KwaZulu. Natal, the province that comes, it will be interesting for everybody. When Vasco da Gama started from Portugal, looking for the way to India, before him, many people tried, along the west coast of Africa. They came to some extent and went back. Another fellow came further down, like you call it Ivory Coast and Gold Coast. All these names came from different adventurers came along the coast, But Vasco da Gama is the first one, who came down across the Africa and then came upwards, Then when he came down, that corner point is called the Cape of Good Hope. That's what he called the Cape Town, Cape Town is the Cape of Good Hope. That is where, he called that, I could come to the bottom of the Africa, now I can find the way to India. That's why that's called Cape of Good Hope. Then he came upwards and came to Durban. When he came to Durban, that day it was Christmas. He came to Durban on a Christmas day. He called it Natalia. Natalia means, Christmas in Portuguese. That's why the province got the name Natal. And from there he went further up and came to Mombasa in Kenya, what is now. That is where, he met the Gujarati business people who already they are coming with a much bigger ship than Vasco da Gama. And then, he followed them coming to India. See, Indian showed way to Vasco da Gama to come to India. He didn't find way to India. And he was shown way to India, but rest of the story I don't know. I'm not here teaching the history. I came for chemistry. Now, okay. Coming to the chemistry, what I'm going to talk about, some of the aspects of the materials. Mainly I focus on the materials, what aspect of it, where we use those materials as catalysts. And I will teach some basic chemistry and also, fundamentals of chemistry, whereby, it is useful for everybody. Nanoscience, we know nanoscience, the particle size, how the particle size is important, and then because nanotechnology, I need not to emphasize more on what is the nano, the main advantage of nano is that for same material, by going to the nano size, you can get more surface area which you can utilize fruitfully and beneficially. That is, the properties. The nanotechnology is everywhere, in every aspect of the life, whether you call it the technology or security or everywhere, biotechnology, food and agriculture, nano is used in everywhere. Now it comes to, when you are talking about nano is good, nano is also bad. If you don't use it properly, nano has the problem, lot of serious problem. As you know, at one stage, everybody used to have the asbestos sheets as the roof cover. Now that is forbidden. Simple reason is, nanoparticles of asbestos, it causes, the asbestos is what it's called, and it is quite a serious problem. Now, no more we have the asbestos sheets. Disposing the asbestos sheets itself is a problem. Similarly, nanoparticles can be used, but you have to use carefully, you don't lose them, okay? And talking about the green chemistry, this is one of the basic principles of teaching, the 12 principles of green chemistry. As you see, the atom efficiency in this using, and then, less hazardous chemicals for the synthesis, otherwise, no wastage, and safer solvents, and like that, number of all those 12, what I want to show is all those 12, much extent you can achieve using catalysts. Using catalyst, now I'll show you how we use the catalyst, and catalysts are not a new thing to anybody. We have the homogeneous and heterogeneous catalysis. Heterogeneous means, different phase materials, and homogeneous, everything in one phase. And homogeneous catalysis is, is known for centuries. People have used all the time homogeneous catalysis. It's quite efficient also, and mechanisms are very well understood. But only the problem is homogeneous catalysis, you lose the catalyst after the reaction. Very difficult to recover that catalyst, and many times, catalysts are expensive. Nobody wants to lose the catalyst. And the differences between homogeneous and heterogeneous catalysis, as you can see, very good high rates with the homogeneous, and normally poisoning is rarely that happens, poisoning, high selectivity, and you achieve the mild conditions. That means, at moderate conditions you can get the reactions done. When it comes to heterogeneous catalysis, easily separated because the catalysts are different phase, and then you can recycle and reuse. Sustainability is great, and then it has the long service life, and mechanisms are not that understood previously. Now if you can achieve high rates and make it robust to poisons, and then to high selectivity, if you can achieve all those with the heterogeneous catalyst, then what I'm trying to say is, you can use heterogeneous catalyst to full benefit. And we have the various materials we use based on the pore size, microporous, mesoporous, and like that. Every material has got different properties and different benefits out of that. Depending on what you need, we do the choice of these materials. When it comes to catalyst, why we use the catalyst, not to make only the reaction faster. Many times you have 2 or 3 reactions occurring simultaneously, but you want only one, no side reactions. That can be very effectively achieved by choosing the catalyst. That's why selectivity, efficiency, and then ability to work under mild conditions, and no environmental eco-friendly, and recyclability. These are the best characteristics of the catalyst. And I'm going to talk mainly about the mixed metal oxides and how they used it in different ways. And I have a number of examples. We did a lot of work in this field, but I will go through a little faster later on that, how we applied it. Now, mixed metal oxides, combination of the 2 metals, it is almost like, sometimes I give the example, why you need the mixture, when one can do, why should you use 2? I give a simple example. At home, you have got some work to be done. You need a plumber and an electrician, to fix the job. By bringing 10 plumbers, they won't be efficiently do the job still, they do faster, but the quality is poor. You can't bring 10 electricians to bring the job, they don't do this thing. By bringing 1 technician and 1 electrician and 1 plumber, they do the job cleanly, and you got the job done happily. That means, the combination is the thing, efficiencies of the things to get your job done when it is little more complicated. Now, another thing, when you look at the periodic table, there are highly acidic metals and weakly acidic, basic, and amphoterous, variety of the things. You can choose the materials with the different qualities when you choose the your catalyst materials. Now, as we said, importance of nanocatalyst, as I said, we use that finer particles that to be used. That means, our principle here is, we use the support material with nanoparticles on the support material. That's what our principle is. That means most of the times the expensive metal is, used in small quantities as the support as the minor material, which is the active material. Now another thing also is, the mixed metal oxide, the advantage of you having is, they are more sustainable. You can use longer period than a single metal oxide. Now I'm going to give you some examples of the green synthesis using the different catalyst materials. And then, our aim is, high atom efficiency. The reactions I'm talking about are almost all, 100% carbon atom efficiency. All the carbon molecules will go into the final product. Whatever we are using, nothing is wasted. And very atom efficiency, normally 95-96% in every reaction. And highly selectivity, only single product. And use the available materials, the starting materials you have to choose. And one-step process, multi-component reaction, and safe chemicals. And then you have the excellent yields. And then, as I said, eco-friendly. All these characteristics I show in all the reactions what I'm going to show you. Multi-step is, single-step reaction, multi-step. In the multi-step reaction, you do one step and take out it and then go to the next step with the other chemicals. In the single-step means, put everything, you do the mixture will give you the final product in one go. That means no separation, nothing, no solvent, no chromatography, everything. You got the final product, take it, wash it and use it. That is the sort of approach. Okay. Now look at it, here we have the silver oxide on zirconia, and in this one, it is used for pyrimidine derivatives, and 12 novel, most of these materials are again tested for their activity, and there are some papers on that also, and I'm not talking about the activity here, only I'm talking about the materials used, and then the sort of the products you get. That is the one of my emphasis for you. You see, this is one slide, but as you know, it takes about 3-4 months to 6 months, for someone to produce this work. You use different combinations and choose that, and finally, although you can design the catalyst most of the times, we choose the catalyst by experience rather than designing, Now in this case, we use the 1%, 2.5%, 5% like that, of the gold or silver on zirconia. And then you look at which is ideal. Sometimes what it happens in the nanoparticles, when you take too little, that is not sufficient. And if you take too much, then agglomeration of that aggregation, you won't have that nanoparticle characteristic. That's why you have to use the right ratio whereby you have the high uniform distribution of materials in the nanoparticle size. And now like here, you see, yield is 90 to 96%, short reaction times of 30 minutes at room temperature. Your solvent is ethanol, and then again, it is reusable up to 6 times with no loss of activity. Even after that you can do, but there will be some activity loss. And conventional reaction with sodium hydroxide, it takes 6 to 8 hours with 45% yield, means 55% of material is still there. You have to recover, you have to use the chromatography. But whereas here, with the 96% yield, very little is left, and your product comes out, and take it out, wash it and use it. This, from here onwards, only materials will change, what the products are changing, but process is very similar. Bear with me, I'll go through fast because I'm told, I'm not given too much time. This is ruthenium zirconia, and to get the novel functional derivatives and pyridine derivatives, all those are new molecules, 90 to 96% yield in 20 minutes reaction time at room temperature, ethanol as solvent, very similar thing, Now conventional reaction reported, best was reported was with triethylamine as catalyst, to homogeneous catalyst, 8 hours and 64% yield. This is bismuth oxide and zirconia. We did a lot of work on zirconia, but let me go through that. All that, fully characterized, we can see how homogeneously the particulate is distributed on the surface. And then you see that one, the yields are very similar, 90 to 96%. This particular reaction is at 80 degrees and 45 minutes, a little challenging reaction, but still water is the solvent here. This one is the functionalized zirconia, no other metal on that one. In this particular case again, you have the mixture of water and ethanol, and you have the at 70 degrees in 3 hours activity yield is 80 to 90%. Now in this particular, ruthenium hydroxyapatite. Hydroxyapatites are, that is the bone. Our bone is made of hydroxyapatite. Whenever you have the problem, they say calcium deficiency is, is indicating that, your hydroxyapatite is not strong. Okay, that is bone contains that hydroxyapatite. That is very good. The reason is, very nicely you can load the variety of the materials into this one. And this one, you can see 2 series of reactions we studied. And both the reactions, they normally, even you see the bottom, conventional reaction at reflux conditions with the acetic acid and stannous oxide as catalyst, it takes 1 to 2 days for that reaction. 1 to 2 days, that means, you forget even what you did those days. Now, in this one, in our reaction, you can see that one, the reaction in 30 minutes, less than 30 minutes, you finish the reaction with 88 to 97% yield and excellent yield. And you can see the material, the particle size is about 20 to 50 nanometers, which is spread out. Very, very fine particle. This is another reaction with the magnesium oxide and hydroxyapatite, and very similar reaction, and you have the hydropyrazolopyridines, and with 90 to 97%, less than 25 minutes, ethanol at room temperature. This is another one, nanocellulose on hydroxyapatite. There is a very interesting reaction in this particular case. Nanocellulose is a very good support material even, and you get excellent yields, 90 to 96% in 15 minutes at room temperature. This is another reaction like chitosan, on the hydroxyapatite, and as you see this reaction 86 to 96% yield at room temperature and less than 30 minutes. Now, these fluoroapatites are another materials very similar to hydroxyapatite but with fluorine, but they are quite efficient. They have got they increase the percentage selectivity of the material, and I will show you another example where we showed in a finer way. Here, you see this one is multi-watt carbon nanotubes with samaria duped on fluoroapatite. You take the samaria duped on the fluoroapatite, then you put that on carbon nanotubes. Then one may ask, why should we take so much effort? All those things individually are good catalysts. Everything is good catalyst, but only the thing, if you want to achieve 90%, 95% yield, they give 40%, 50%, 60%. The combination that gives you 90 plus yield, with single product, selectivity is improved and yields are improved. That is what the advantage of having this material and excellent yields. Now here we have a very similar one, in this case titania and fluoroapatite and carbon nanotubes, and you see 91 to 95% yield at room temperature in 15 minutes. Another type of materials are hydrotalcides. Hydrotalcides are nothing but the paste powder. The talcum powder what we use is a hydrotalcide. That is so cheap material. That material can be used as excellent catalyst, and here you see that one, in less than 1 hour, 89 to 90% yield, whereas the conventional reaction gives you after 8 hours only 54% yield. And this is another zinc vanadium carbonate on the hydrotalcide, and as you can see 93 to 98% yield in 1 hour at 80 degrees, but in water. That is, solvent is water, whereas conventional reactions give you 30% yield at 80 degrees after 6 hours. So much waste, And here we have the gold on magnesium oxide, and for in two series of reactions. Here we use the graphene oxide, functionalized graphene oxide. Functionalized graphene oxide, and next one. This one is an interesting reaction. It's not a mixer oxide. It's simple case of the graphene oxide, loaded with manganese oxide. This is quite good. In this reaction, you can direct conversion of benzene to aniline. Most of the times, it's a two-step process, but you get in straight reaction, excellent 100% selectivity and 77% conversion. That means, it's quite good conversion in one step. Most of the industrial processes are two-step processes. And come to the metal organic frameworks, these are the ones, relating to some extent to luminescence. The metal organic frameworks, there are a variety of the things which can be designed with the combination of your precursors. And then, these ones have the very low density, like the gas capture, etc. Hydrogen capture, carbon dioxide capture, etc. Water pump is used using the MOFs. The MOFs, the advantage of this, you can tune their properties quite well, and in the sense, the size and the porosity of the size, the supermolecule, and you have that, guest molecule in there, and the emissions that are possible. This is where, luminescence arises from the direct organic ligand excitation or the metal centered emission or otherwise charge transfer, such as the ligand to metal charge, like all that. And gas molecules also result in luminescence of the MOFs. But I'm not talking about the luminescence, I'm talking only about catalysis. And these are, MOFs are used in various processes like chemical sensors or light emitting devices or biomedicine, etc. And it has, if you look at, the applications of MOFs, and you can get, variety of the MOFs, and then, they are used in the gas storage or optics and drug delivery or catalysts and everything. But I'm going to give you a few examples of the catalysts. Now here you see this a coordination compounds. Here a 4-component reaction, 4 components put together give you a single product, 90 to 98% yield. No, it's too much for her, And now in 20 minutes the reaction finishes at room temperature so comfortably, you get it recyclable material. You can use that, without. Here another coordination compound, 4-component reaction, 4 components put together, you get 100% carbon efficiency, no loss of carbon, 90 to 96% yield with ethanol at room temperature. Now here we have the MOF. In this MOF, we got 3-component reaction, very similar, all the new molecules in 40 minutes at room temperature, very highly recyclable material. And this is another MOF. Now, eggshell. See, the egg, what you eat every day, the shell can be a very good catalyst. The reason is, that eggshell contains very high amount of calcium oxide, carbonates, and some sodium and magnesium oxide. With that, the combination is a mixed metal oxide. Eggshell is a mixed metal oxide, is an excellent catalyst. You can see here a 4-component reaction. Just you add the eggshell powder and no chromatography needed. You have the 98% yield at room temperature in 45 minutes. 100% of the carbon efficiency, 98% atom efficiency. Very little waste that is going out of your reaction. Another one is, clay chemistry. As clay science is a big, there are journals dedicated to clay. You take your brick powder that can be used as a catalyst. Brick powder, the reason is again the same thing. It has got silica as oxide, iron oxide, aluminum. Those are the main. You have the calcium and magnesium. That means, a mixed oxide, it is doing excellent job. as you know, brick powder in India to be recycled, it is cheaper to use a little more clay powder rather than recycle, but still it is recyclable. Now you can see that on this reaction 91 to 96% and up to 5 cycles, you can reuse it and excellent results. And I think, I'm coming. Finally, as you see that, mixed oxides as the catalyst, you can get excellent results and recyclability in moderate conditions. Now I want to thank the courtesy of the Professor Murthy Garu and then who gave me the opportunity to be here on this boat trip, It's lovely, and you lose your coordination where you are, And then my university, which supports me, and all my students, who put their work. And some of our students, actually, all I put my name just to show that is our work, Really speaking, the publications, when you look at it, first author is the one who really sweated in the lab, and my name I put there, because they belong to my group. And these are some of my postdocs and the PhD students, and it's not all, just now. This one is a message for the younger people, The thing is, a man can succeed at almost anything for which he has unlimited enthusiasm. That means, that is the most important. The reason is, if you haven't got the zeal to achieve that, never will succeed in that life. That's why it is said, if you are aiming for distinction, there is a good chance of at least you get a first class. But if you are aiming just at a pass, at most you get supplementary. That's why, that you have to aim high to be successful in the life. And this is our Durban beach, and it's a blue flag beach. What it means, the government assures you are safe to take bath there and you won't get sick due to taking the dip in the ocean. This is the soccer stadium at Durban, and those people who don't like soccer, they can go to beach again. Thank you for your attention.
Thank you, Professor. First of all, I must appreciate General Gandhi sir, because exactly it took 30 minutes. Generally, every time, sir, please, sir, please, sir, please. They are not given anyone. Sir, if you want mind, can you stand up for 1 minute? Please, come here. Come here. Now you can see the tie is periodic table tie. It tells you how he loves the subject. And thank you, sir, please. And there are, time is very short, but only one question from another my good old friend, Reddy Garu. Please kindly, sir.
It's more of a comment. Anyhow, it's a very good lecture. Congratulations. And one comment I want to make on green chemistry. I want you to make a comment. See, you are talking about the efficiency, very good, in the lab. I taught green chemistry for 6 months. All the time I used to struggle how to upgrade and what will be the outcome. And when you are going to an industry, is it feasible, right, for publication?
Yeah.
Good. Do you have a comment?
No, I fully agree. Upscaling itself is a different technique, and then upscaling, going to the pilot project is another level, But, the thing is, many times, unfortunately, the chemists, stop where the chemical engineer should start. And we being chemists, no, it's a good question and it's a very important question. The reason, finally our aim has to be how we can use in the community, like Professor Chaudhary mentioned that, it's not that what you do, how you make it usable for the community. And I fully agree. In another field, we are working also using the similar catalyst in the water treatment, particularly some of the toxic pollutants you can't remove from the primary and secondary treatment. Sometimes you need a very advanced tertiary treatment. That's where you can achieve very good, and also your catalyst is not contaminating your material. That sort of work we are also doing some, but I agree with you. Thank you for the question.
is a family seminar because physics and chemistry are like wife and husband. The next question comes, who is wife, who is husband? Undoubtedly, chemistry is a wife because they are so much smooth, they are lovable. And in cinemas also we listen always, there is a good chemistry between hero and heroine. Nobody says there is a good physics between hero and heroine so far. Because we are tough, male are very tough, you know the physics is tough, so that we are a other side of husband. And the next question comes, what about the mathematics? They are like children to us because the children never listens our voice. We have to listen to them. Now wife is over, now we are inviting another wonderful person, Dr. Harnath. Professor Harnath is unknown to me till 2018. Now both of us are working together. He is one of my good friend. His biodata briefly reads, but this brief reading is taking the entire day, sir. But let me try my level best. He is a gold medalist in post-graduation at Kakatiya University, Warangal, from where we are staying, 1994. He obtained his PhD from the Shivaji University, Maharashtra. And after that, briefly I will tell, sir joined as a NPL and working as a scientist, different categories. Recently, he shifted in 2018 as associate professor to NIT Warangal due to his family, old mother and father, and at the same time to take care about his in-laws also. And recently, sir is promoted as a professor, and both of us are working together in the same department, adjacent rooms at NIT Warangal. Important awards and medals received by National Innovative Research Excellence Award 2022, Grassroots Innovator Virtual Metal Award 2020, Transfer of Technology Award 2017, Fellow of Luminescence Society. There are 14 to 15 awards are there, but sir kindly permit me to read only few of them. And NIT Warangal presently teaching optical physics and nanophotonics. Recently I think he was selected as a member of ACSIR to review a particular team. Let me come to the citation. 5238 is the citations as in today. H index is 39, I-10 index is 113. Number of total publications including A to Z till date is 2750. Transfer of technologies 3, patents granted 8 and filed 2. And I would like to say he is kind enough to include my name in one patent, even though I had done a fraction of work. In my biodata, sir, that is the only one empty left. Now the empty is filled by Dr. Harnath. Thank you, sir. Scopus Index publications are 275, countries visited 5, awards received 12. Total invited presentation delivered is around 200, PhD completed 7, undergoing 1. So total number of publications, as I told, around 2750. So this takes lot of time to read the one. So sir, kindly permit me for this small one. With this small brief introduction, I will request Dr. Harnath, my good friend, to start the lecture. But sir, you are my friend. Time is 30 minutes for you also. Thank you.
And I thank the organizers also to giving me this opportunity. So actually I planned for some other talk, but unfortunately my pen drive didn't work, so I had to switch over to another topic which is more relevant to Kerala. Development of super hydrophobic and super oleophobic surfaces. When yesterday we came to the airport, we could see the Kochi airport. It is written that it's the world first airport powered by solar. So there were a lot of solar panels that were existing there, and the main problem of having this solar panel maintenance is due to dust. If you have hydrophobic surface over which, then it can be act as self-cleaning. Otherwise they have to deploy so many people to clean every day. So that's the main thing. So just I wanted to put some light upon these hydrophobic surfaces, which has many other things also, and oleophobic also, super oleophobic also I would like to say next. So this is my institute. This is the institute website, Department of Physics website, and my own profile. So you can go through our research activities from which, or you can just scan that one, then it will take to that website. Next. So what is superhydrophobic? Superhydrophobicity usually we measure with respect to the contact angle of water droplet with respect to the surface. So it is like it is a surface that is resistant to basically for water, so it will not wet it. Okay, next. So it is basically the affinity, like if you use our clothing and other, if it is super hydrophobic, means if the critical angle is more than 135 degrees, so then you can have it will be repelling water. Next. So you can learn this type of surfaces from the lotus leaf. You see that it is not wetting. So we can gain lot of ideas from the nature, like how it is happening, how it is repelling water. So if it is repelling water, it can repel dust also. That's the active. Next. So if you carefully see through the electron microscope, then you can see that the droplets, even though there are certain small dust particles sitting over that, just sprinkling of water or with a little vibration, it can pull down all the dust which is there. No need to have a wash and other things. And in southern India, you see that most of the temples, they use leaves, banana leaf or lotus leaf. On that they give the prasada to the deity. That is because it doesn't allow any bacteria or virus to grow, because for bacteria or virus to grow you need to have moisture. So here it doesn't stick, water is not sticking, even the bacteria is sitting on the leaf, so that will die without having the moisture and sufficient oxygen. So that is the purest thing. So we are offering anything to God on a very clean surface. So that's the idea behind that. So how it is showing this type of banana leaf or lotus leaf, how it is showing this type of behavior is based upon the microstructure. It has like pillar type of microstructures that are there, that are present over it, and it does not allow, because you know the nanostructures have less oxygen, so it will not give any sufficient oxygen to grow for this bacteria or viruses. Next. So you can how to determine the hydrophobic nature. It is from the contact angle measurement we can see, and if it is super hydrophobic, like nothing is sticking to that one, you can see the bouncing of droplet in slow motion. You can see that it is completely bounced back without any touching to that. Next. So these are certain surfaces and these are certain applications, like you see here. You can mix this type of super hydrophobic materials into various like in building industry, you can put it in bricks so that nothing can stick it to that, and life will increase. Super hydrophobic surfaces, tissues, or even shoes, leathers and other things, you can have these type of coatings. There are many applications apart from the solar things. Next. So there are various theories that are governing these super hydrophobic surfaces. Basically it is three types of theories are there. Next. So this is how the contact angle has been measured with respect to the surface and the droplet of water. Next. Quincke's method. It's called Quincke's method, and these are the three various theories. It's a usual contact angle measurement, and that is Wenzel surfaces and Cassidy-Baxter's surface. So here, if it because this is very ideal case where that surface is very flat. In most of the cases, it will be having zigzag type of structures, or where some air will here there is no trapping of air, whereas there Cassidy-Baxter structure, even the pocket of air between the water molecule and that one also will be taken into consideration. Considering all these things, the contact angles have been measured. Next. So this is about various applications of this and the theories, how it can go through. Next, this is about the Wenzel state where no air bubble is taken into consideration. Next. In this one, air bubble inside the surface also will be taken into consideration. So how to create this type of surfaces, like nano micro technologies we can make. There are certain laser scribings also with which we can make such type of hydrophobic surfaces. Next. So even in submarine things also, they like to have hydrophobic coatings on the missiles that they fire, because that will have very the affinity between water and the surface is very less, so that they can go through for longer distances. That's the requirement of marine people. So here also that coating would be there on that. So these are various applications. Next. So this is about the condenser cooling systems, like in air conditioning. Next. And these are some laser created hydrophobic surfaces where everything is reflected back. So I wanted to give certain applications, and this is our research work what we developed recently. This is about super oleophobic surfaces. Super oleophobic is nothing but oil repelling. See, in most of the kitchen areas you see, or in refineries and all, you see all the walls and the ground, it is everything is sticking with oil. So can we have nanoparticles that can repel oil, but hydrophilic, means water loving, so that we can clean with soap water and we can clean it, but no oil will stick to the walls of the either kitchen area or in the refineries. So that was the main thing. We have used a simple ultrasonicated method where you can take aluminum foils and then sonicating in a with particular energy, and then you can get nanoparticles of aluminum hydroxide. You can create it, and we have mixed it with the various other materials, like we have used next. We have used with various other surfaces. For example, we have used white cement, which generally we use it for various applications. Of course, the nanostructures, it is showing like flake type of structures, and we could measure some photoluminescence and other properties also, that one. But the actual application of this oleophobicity is what oil repelling. So that we are more concentrating rather than photoluminescence and others. So this hydrophilic and oleophobic combination in one nano material, at the same time it is accepting water, but it is repelling oil. So that was the major thing which we could deduce this one, and we could measure using Quincke's method. We can measure the contact angle, and we have measured with various types of oils, generally coconut oil, olive oil, castor oil. These are the oils which we use it. At the same time, we could measure how much it is the contact angle is being produced with that one, and the best one we got it. That next, see, oil drop on this nano flakes, aluminum hydroxide nano flakes mixed with white cement. So with that one we could see that the oleophobicity is less, and compared to the best super oleophobic thing we could measure with castor oil. So castor oil is completely, you can see the spear, the best spear you will get it, the more it is repelling oil. So for the various viscosities we have measured, because we were not intentionally we were doing this research, but we were doing for some photoluminescence applications, but this is the new thing which we could find out from that. So for more viscous oils, there was a lot of this contact angle was much higher, and it was just repelling. So all viscous oils, wherever it is being used, so that can be having this type of property. Next. So we could study certain chemistry behind that, how it is being interacting with water. And one application what we have seen is like in emulsions, water oil mixture would be there. So having this material coating on a filter paper, we could see that we could easily separate oil and water. So water is being, of course we use certain vacuum also. So we will get clean water, and then here you can get the oil which is there on the filter paper itself. So this is basically like in oceans, suppose there is a tempest or cyclone type of thing. to reduce the surface tension, they spill all the oils into the ocean area, so that the turbulence will be less. So again, how to retrieve that oil? So this is one of the methods with which we can retrieve the oil, the waste oil. Next. So this is just the chemistry, how it is interacting with the metal membranes and other things. And other applications are also useful, like anti-fogging on the car, this thing, and soap-free self-cleaning, highly desirable for industry and domestic walls also we can have. And in conclusion, I would like to say that these aluminum hydroxide nanoflakes were developed with this super oleophobic property and hydrophilic property at the same time. And there are many applications related to this hydrophobic and super oleophobic in near future. Next. And finally, I would like to thank organizers Dr. Anjana and my friend Dr. Gopakumar and Professor Murthy and Dr. Janalgata sir and Dr. Dinkar sir and all others, and Reddy sir. So having invited me for this beautiful event, and thank you very much for your patient listening.
Sadhana, you are really my true friend because you took less than 30 minutes. Now, this is a time for questions because sir has given saved some time. Questions. Sir, ready sir, please.
I have, first of all, congratulations, it's a beautiful work. I have I need a clarification, personal clarification. How did you choose the starting material? Aluminium. Aluminium is having a beautiful property. Is it the reason or you have something in mind? Then the second part is mechanism I want to ask.
Sir, actually it was a accidental thing which we got that super oleophobicity property. Actually we were working to make aluminum nanoparticles. So it resulted aluminum hydroxide nanoparticles, and of course photoluminescence and other things by rare earth doping and non-rare earth transition metal dopings also we were doing. Suddenly there was a, accidentally my student, they could found out that, sir, it is repelling oil. So something has spilled over and the surface has just repelled oil. Then that attracted us, then we could study little more into detail about that. Oil repelling is one of the major things.
Other than measurements,
Yes, sir.
measurements is consequence.
Yes, sir. Yes, sir.
What is the basic explanation for this dual behavior of one is on one side is hydrophobic,
Hydrophilic.
hydrophilic, water is attracted.
Yes, sir.
Other one is oleophobic.
So it has two different when it is mixed with certain cement or some other surfaces. As such, aluminum hydroxide nanoparticles are not showing this behavior. As Dr. Janalgata sir told, the combination, like it is when it is mixed with the usual cement or white cement, so it was showing this type of property. So there
What
could
you
be.
observed, sorry to interrupt.
Yes, sir.
What you observed you are telling. I said, what is the mechanism?
Mechanism
What is-
still
what you
I
observed-
can
what you observed, you
yes sir,
observed.
yes sir, I understand that mechanism is
If
still
you have an idea.
it is still complicated, because what we could see is it is having hydrophilic at one side and hydrophobic at other
It
side.
is aluminium. Basically,
It's aluminium.
Third group.
Yes, sir.
You can have that gelatinous crystal. You have the both acidic and
Yes, sir, yes, sir.
property. So it can act as hydrophobic.
Phobic as well as
oleophobic.
hydrophilic.
That is possible. Anyhow,
So
on my knowledge.
no, that's a interesting thing which we would like to pursue that in more detail.
Yeah, sir, please.
This question is not for you, sir, Dharma sir.
Yeah, I am also
Since-
having a question for sir.
Since it is a dual function, so sir, this material used as a heterogeneous catalyst or homogeneous catalyst?
That one you told.
Heterogeneous catalyst.
But when it is mixing with the solvent, why not it is homogeneous?
Mixing with, you see what it happens, many a times, these reactions are not only your chemicals in the water, it is heterogeneous, not homogeneous. That's why, system is heterogeneous. As long as you can recover that, it serves your purpose.
Yeah, as a chemist, your material has a more catalytic applications. So that's why.
No,
Thank
it's
you.
Okay.
Should I answer?
Yeah.
Yeah, please. because such a big problem.
No,
Totally people are vacated the capital of South Africa
no.
just because of
Cape Town water problem. No, it's
Cape Town.
Cape Town water problem. I want to tell you one thing, In India, how many houses have got 24 hours water supply? How many 24 hours water supply?
no single house.
Unlimited. Okay, that's one thing. Many people say, yeah, we have the supplies are there. It's not natural municipal waters. In Cape Town, never their water supplies were stopped. 24 hours you get the water. 24 hours municipal water supply, that is drinkable water. That means you can collect that water from the tap and drink. There is no treatment further needed. That is one thing. What they have is, the problem is, due to the rainfall is low, the water supplies are low. What they said, look here, we supply the water, it is your responsibility to use wisely. If you use more, the charges are much, much higher than your minimum requirement. That's what they did. Never they stopped the water supply to anybody. To add to that, many, what you call farmers, they stopped using the water for agriculture. They allowed that water to go into municipal supply so that the municipal water is not interrupted. That way, sometimes the publicity it gives a wrong image. I saw that some of the videos, they are showing buckets and those things, they don't happen. That is not there. 24 hours water supply is there in Cape Town. Never it was stopped.
Yeah, thank you, sir. We are thanked to Indian government because Indian government never gave us 24 hours water. So there's still a lot of water is there in India. Thank you, Professor Anna, for giving a wonderful lecture because you are giving the right lecture at the right time. Development of super hydrophobic, super leophobic surfaces is an encyclopedia of the knowledge. And generally you might have given 2,500 lectures, other things on the ground. I think first time you are giving a lecture on the floating water. Thank you once again for your lecture. Sir, join with me to a small memento from myself and on behalf of organizing committee. Sincerely thank you very much, sir. I requested Dr. Prashant Kumar to write a few sweet words about you. Otherwise, I will keep your head and I will add my biodata. So he's told I am a diabetes, I don't want to give much. So his biodata or resume given is very small. Research interest, functional organic materials, MSc from University of Hyderabad, PhD from CSR NIISC, Trivandrum. I think he belongs to your place. Postdoc from Japan, scientist. Right now, sir is working in the Indian Institute of Chemical Technology at Hyderabad. So there are several awards to the sir. Number of publications around 50, PhD completed around 5, projects completed around 6 of 1.5 crores. The DST Inspire Faculty Award 2015, Associate Fellow of Andhra Pradesh Academy of Sciences 2020, and Nanoscale Engaging Investigate Award 2020. So with this small one, I request sir to deliver. What is the topic? Yeah, I think he's the right person giving the right talk. Now I think I request Dr. Prashant to deliver his talk. Sir, once again, he's my friend from yesterday onwards, but the time is constant for 30 minutes. Sir. Thank you. Please kindly start.
Just for giving an opportunity to talk about my work. Actually, I'm not mainly focusing on the luminescent materials because we are mainly working on the photovoltaic materials, like particularly light harvesting materials. Since this main conference is organizing on luminescent materials, so I would like to discuss about some of the materials can show the luminescence from our whatever making in our lab. So first of all, of course, I have done my PhD with CSIRNist Professor Ajay Ghosh. I think many of you know. Mainly working on the self-assembly and conducting gels, organic gels. After I finished my PhD and postdoc, I joined in IICT and started working on the photovoltaic materials. and also collaborating with Dr. L. Giribabu. I think tomorrow he is going to give a lecture on the photovoltaic materials. Let me talk about what I am going to discuss with today. Oh, sorry. Okay, can you move on? Slowly. I think Professor Murthy, I think he already given the introduction about how you are seeing the luminescence everywhere like today. Majority of today what we are seeing is light emitting diodes. Of course, whatever you are now present, you are sitting also light LEDs are everywhere, white light emitting, blue LEDs, green LED, everything. When you look at the device structure, how we are making the device, like whatever we are making the substrate and coating on the anode and cathode materials, below that we are making the semiconducting layer. That's what we are making. The semiconducting layer mainly consisting of either, it can be either inorganic or organic materials. Actually, I belongs to the organic chemistry, so we try to make some kind of organic materials. Inorganic materials, what happened is that now we are seeing a lot of materials, of course, showing the very high efficiency. The main problem is that always when you make this material, it's very difficult to what is called developing in our lab. Particularly, it cannot be soluble easily, and also it's like abundant materials. Always you have to get like naturally. It's very difficult. So that's why people started looking into the organic materials. The organic material advantage is that it's like easily you can make in our lab because of everything is depending on the organic chemistry. Make some materials, benzene or type in whatever available. We can get it and mix together and make some organic materials, and we can flexible. How we can make flexible? When you want some kind of property, we can simply change the functional groups or structure. That's kind of flexible molecules. We can fabricate very easily. We can easily soluble any solvent and flexibility, as well as we can make the thin films when you go into the solid state devices. That's kind of advantage we are seeing now. That's why now I am going to talk about the organic light emitting diodes. Of course, we are making the materials mainly. And today market, we are looking into the market. What is happening is many of our LEDs like Samsung or LG, Apple, wherever you go, now OLEDs marketing is very high. It's almost like competing with inorganic materials. That's why now we are seeing the $300 billion. Now it's working on it. Go to the next slide. These are some of the materials still now reported in literature. Today I am going to talk about one is the porphyritic kind of materials and also DA systems. Why we choose the DA systems? Generally, when you look into the DA system, what is happening? It's containing the DA means donor and acceptor. When you mix together, donor always it will ready to give the electrons and acceptor always take the electrons. These kind of materials, can you go to the next slide? When you look at the ion BT, you can see the imidazole. Here we are using this kind of the indole molecule. This can be act as a very good donor, and benzothiazole act as a good acceptor. When you mix together, what is happening? One is ready to give the electrons, and another ready to take the accept the electrons. When you put them together in a single molecule, what is happening is when you apply the light, what is happening? Both can generate the electron and hole pair. When you look into the diode combination, what is happening? Electron hole pair combination should take place. When you apply light, there should be electron and hole transport takes place. Where it combines, it produces the light. That is called, we are seeing the mechanism. So our main intention is that we want to create a material consisting of donor and acceptor. So interestingly, what you observe is that when you synthesize in our lab, actually we are synthetic plus materials. When you synthesize this material in our lab, interesting what you observed is that when you mix the donor acceptor, what is happening is that it's always some kind of color chromism will take place. When you put any solvent, when you apply light, it started changing the color. That's what we observed, and also it's showing the emission also. And when you apply different kind of light with different kind of excitation wavelength like 320 to the 500 nanometer, the changes of the color, what you observe is that pink to the orange and orange to the yellow. This kind of the stable form. If you are not applying any excitation wavelength, this cannot be forms. This kind of changes we cannot observe in this case. Can you go to the next slide? These are the changes we observed by conforming by, particularly we study with the UV visible like absorption spectroscopy as well as the fluorescence spectroscopy. Of course, if you know the Jablonski diagram already, Professor Murthy already discussed about that. When you want to see the transitions, electronic transitions from ground to the excited state and excited state to the ground state, we always need to check the UV visible absorption as well as the emission studies. So we have done the absorption studies initially. What is happening is that how these molecules from ground to the excited state, what kind of changes we observed in the energy levels, like where it is absorbed. That we can see that when you take the simple donor acceptor, when you compare with the DA system, since there is a conjugation length as well as the DA phenomena, there is a extended absorption we observed when compared to the donor to the acceptor. This confirmation we can clearly see from here is that when you excited a different wavelength, like 320 nanometer and 500 nanometer, we can clearly see that what changes we observed when compared to the initial to the 320 nanometer. There is a shift in the band. We can see that there is a shift in the band at higher wavelength. We can call it as a bathochrome shift. I think you might have heard in the absorption spectrum. What is happening is that there is some kind of oxidation in molecular system takes place that causes a shift in the absorption spectrum. And subsequently what we have done is that we change the solvent, whether this molecule having any effect in the solvent. Then what we have done is that chlorinated solvents to the non-chlorinated solvents. Particularly this kind of phenomena we observe only in the chlorinated solvents, that we can clearly see from this spectra. And this is the visual color change. What we observed is that initially this molecule exists in a pink color. When you apply the light, it started changing into the orange to the yellow color, and this is a stable state. Can you go to the next slide? This is the emission spectra, and what you have shown in the ground state phenomena is we can see only in the absorption spectra. When you go to the excited state phenomena, there we have to study the emission spectra and lifetime analysis. From the emission spectra, it is clearly shown that there is a emission intensity is very high for the orange color. When you come to the yellow color, it's showing the low intensity compared to this one. And this is the corresponding lifetime analysis. We always check the emission as well as lifetime analysis to see that how when you excite the electrons, how long it will take place in the excited state. That you can confirm by using the lifetime analysis. This is the lifetime data to confirm that these molecules can be easily tunable when you apply the different kind of excitation wavelength. Can you go to the next slide? And also we study with the different analysis like solvent, and another one is the concentration dependent analysis. Because of when you want to check this one, at what wavelength and what solvent is changing. Another one is that how much concentration we can improve the intensity of the light. So that you can clearly see that it's a millimolar concentration. It is slowly increasing the emission rate that we confirmed from this analysis. Can you go to this? Yeah. This the overall phenomenon of this work is that we made this material like a DA systems. When you apply the light, we can easily tunable by applying the different kind of excitation wavelength. It can change from one color to the another color by simply controlling. There is a proton here. You can see that there is a protonation and oxidation takes place that causes this color changes. Can you go to the next slide? Yeah. Further, what you have done is that we started working on the porphyrin material. Porphyrin is a very versatile molecule, and it's not. I think we are seeing wherever it's like a green color in the leaves and blood, hemoglobins, wherever you are seeing the porphyrin materials. And this is not only applicable in one chemistry like physics, materials and biology. Everywhere we are using the porphyrin material. So in our lab, we are expertise in the synthesizing these porphyrin materials, and Dr. Elgiri Babu is expertise in how we are making the porphyrin synthesis. Once we associated with him, we started working on the porphyrin molecules, and these molecules in a pink color, and we modified this system with pyroxene derivatives. Interestingly, what you observed is that when you make this molecule, put in a solution, upon sonication, what is happening is there is a protonation takes place. Since this nitrogen is very free, it can easily protonated in sonicated state, and this causes color changes we observe. That you can clearly see from the pink to the green. Interestingly, what you observed is that when you done in the microscopic images, initial state it is forming the very crystalline structure that you can clearly see like a star shape. Upon protonation, it is completely changing to the crystalline to the amorphous nature, and clearly see from this kind of sphere kind morphology. This is due to the when the molecules are stacking each other, it started like different kind of aggregates. One is the H type and J type, which causes leading to form like a affecting on the crystalline phase transition. Can you go to the next slide? These are the initial parameters to study that how these molecules affect on the absorption and emission properties. We have done the detailed investigation on the absorption and emission properties to check that whether these molecules are changes in the optical properties, particularly upon sonication and time dependent. Interestingly, what you observed is that in sonication there is a shift in absorption spectra. Keeping the long time, it can be reversible. That's what we observed by checking the absorption spectra, and this can be reversible for how many times we have done so many times, and it can be reversible. Can you go next slide? And when you want to confirm that this kind of phenomena, emission study is also very important, because of when you look into the emission and sonication, there is a significant quenching in the emission spectra compared to the initial spectrum. Upon reversibility, again it can come back. From this, it's clearly confirmed that this molecule can easily tunable upon protonation by sonication or with respect to the time. This is further confirmation by the time correlates single photon counting experiment like a lifetime analysis to see that changes in the electronic behaviors at ground state and excited state levels. Can you go to the next slide? Yeah. These are another molecules like thalocyanins. Of course, previously we are seeing the porphyrins like tetraperiodic system. This is the analogous of another metal is thalocyanins. In this case also we observed similar kind of phenomena. But here what we applied is that we apply the light. Because of the light is the everywhere source is there, sunlight is there, we have a lot of energy. Can you go next slide? When you apply the light in these solutions, we have made the three molecules. You see, three molecules color you can see here is that this is before light. This is the corresponding absorption spectra. When you apply the light, there we observe that there is a quenching in the, there is a bleaching in the absorption spectra. But when compared to the 1 and 2 molecule, 3 molecules showing the distinct changes compared to the 1 and 2. That from this we confirmed that when the molecule consisting of the triphenylamine, which can easily oxidize, that's why we confirmed by using the UV visible light, particularly in chlorinated solvents. Why you observe this particularly in chlorinated solvents? These chlorinated solvents easily produce the HCl when apply the light. This HCl causes the protonation in our molecule. Since our molecule consisting of the nitrogen group, which can easily give the protonated the molecule, like easily donate the electrons. Can you go to the next slide? This further we have done the excited state phenomena to check this phenomena works in excited state level, particularly under light illumination. What you observed is that when you apply different kind of excitation level, like 645 nanometer we used here with different kind of time scale, what you observed is that there is a quenching in the phenomena for 2 molecules. Like 1 and 2 we are saying that there is no significant quenching phenomena we observed here, but particularly for molecule 3 there is a emission is gradually decreased. From this we can observe that the molecule consisting of the triphenylamine easily undergo the mixed valence state generation, that we clearly confirmed from the absorption and emission parameters. And further we started working on the self-assembly because of our main motto is that we are self-assembly group. We are making different kind of structures to generate the nanotechnology, like what we will discuss now, create the different kind of nano shapes, how this is going to affect on the organic properties. Here also we have done some ground state and excited phenomena. Then we studied the nanotechnology behavior, like nanoscopic, how this molecule behave on surface. Here what happened is that we designed 2 materials. One is that the molecule is a porphyrin with a hydrogen bonding moiety, whereas other cases having the bead like a benzothiazide, which can act as an acceptor, and this porphyrin act as a donor. And initial study, what you observed is that these molecules, when you keep in the previously what you observed chlorinated solvent, this molecule started changing the different kind of phenomenal color changes. In this molecule, when you put in the chloroform, this is only exists as a monomeric state. When you put in other solvent like non-polar solvents, like we used as a cyclohexane, it started aggregating. Actually, that is the interesting phenomena. This molecule started aggregating, and you can clearly observe that what changes we have seen in the ground state phenomena. You can see here one band is upward at 400 nanometer, another band appeared at the 600 nanometer. Upon aggregation, there is a bathochromic shift, means red shift we observed in this case only in the aggregate state phenomena. Can you go to the next slide? And further we have done the detailed investigation to see that only particularly in one solvent like chlorinated solvent or another solvent can change this kind of phenomena. And we studied by using the UV visible as well as the emission studies. From the emission studies, the first molecule where you are using the P1 molecule is not showing any changes. You can clearly see that when you increase the temperature from 20 degree to 80 degrees centigrade, this molecule is not aggregating in any solvent. Can you go to the next slide? But interestingly, the second molecule where we created the long conjugation having the BDT like benzothiazide, this is showing the very good aggregation. That is, you can clearly see from the schematic representation here. When you exert that 450 nanometer, upon increasing the temperature from 20 to 80 degree, at low temperature these molecules are aggregating and there is a shift we observed. But at the high temperature, what is happened? There is a breaking the aggregates, that leading to form like a monomers. Monomers molecule is as a molecule itself. When the molecules are aggregating, it can be assembled together, forms like by using various supramolecular interactions like hydrogen bonding and pi stacking and van der Waals interactions. It forms like a different structures. Can you go next slide? Yeah. These are the lifetime analysis to see that how this changes when you go into exercise state. How this lifetime will vary. This you can clearly see from here. When the monomer molecule exists as a single exponential decay, when the molecules are existing as a aggregate state, it is showing the bi-exponential decay. It means there is a excessive lifetime changes. We can see clearly from this analysis. Can you go next slide? Yeah, these are the microscopic analysis we can found by using scanning electron microscopy and transmission electron microscopy. Initially, this molecule exists as the nanostructures, like you can see here, nanosheet at low concentration. Upon increasing the concentration, what you observe is that this nanosheet becomes the nanofiber. This is very important when you go for the any optical device applications. So, with this, I would like to conclude is that, see, our main objective is that we create some kind of donor and acceptor structures. There we can create the electron hole pair to generate the emission as well as the absorption properties. And moreover, that what you would like to do is that we want to create some kind of nanostructures which can tunable their electronic property. That is more important when you go any device applications. That is our main conclusion like this. So finally, I would like to conclude is that I would like to thank our Dr. L. Giri Babu, who is our association with our doing this kind of work, and these are the present and former members working in this area. And finally, I would like to financial support CSIR and DST. Thank you very much.
Thank you, Dr. Prashant, for integrating physics and chemistry, because new education policy is asking always for integration courses, and your talk on luminescence for organic materials, donor accepted system. One or two questions from audience. Anybody?
I can ask, but I'm not an expert in your field. Okay. It is for my clarification.
Yeah.
For my clarification.
Sure.
See, you showed a red shift, material manipulation. It has become very sharp. You are not I get a feeling you are not accounting for the total intensity. Where the material has been. One of the pictures, five slides back. 5 slides back or 6 slides back. One more. Where you have shown red shift? That is the area I want.
Where?
Red shift. Where the promotion?
Absorption.
After, I know.
Yeah.
I think next one. Somewhere, too sharp I think to believe in a UV region. Because the too sharp region, what could be the reason? How the energy levels have become clear to have the transition?
Okay. Actually, maybe when you talk about the porphyry, when you talk about the porphyry, we can clear
one more.
pi to pi star transition you are talking.
One more slide down. I am not locating. All right. For my education, I am asking.
Actually, when you look at the pi to pi star transitions, that energy level is always low, and you can see the higher intensity. I think this is known in the already.
Textbook.
Known in the textbook.
Textbook. Now, what I am asking is, in the same.
You are talking about the shift in the bathroom.
And shifted one intensity is too sharp. I mean, too narrow.
No, that is not the bathroom shift. What is happening is that these molecules are protonated actually. So there is no changes in the molecule. Just it protonated, it causes shift in the absorption spectra. So that's why it is affecting the electronic levels.
And also in your P1, P2, whatever you have shown, I don't know much in the right.
No, P1, P2, I just give the names.
That's all.
But it's because of
next. For my clarity. Next. Yes. I am more interested in the instrumentation. Next.
This one.
One more is there. If there is a delay, quite a bit of inordinate delay in the decay. With a blue color you have shown. Probably next one. Time spectrum. Next. Green color. How do you explain this delay?
You mean this one?
Material.
This one, what you can call it as there. Actually, when the molecules exist as a monomers, like it's a single molecule. But when the molecules are bunching together, it forms like aggregates. So what is happening? There is a localization.
I understood.
It's not like a single molecule, mixture of molecules. It can be either energy, electron transfer, or aggregation.
Once again, on behalf of organizing committee and on behalf of my personal, everybody, once again sincerely thanking Dr. Prashant, and I request Anna sir to join with me in presenting the memo. The morning session was totally delayed in view of this one from public demand. In view of the delay of the morning session and from public demand, there is a small change. The fourth talk by Dr. Madhu please kindly permit us to postpone this photo after lunch because some of them are falling. And Murthy sir told one thing, because it is houseboat, nobody will miss from the houseboat. And I came to know somebody is missing. So hence it is proved even from houseboat also somebody can escape. Now there is a small break for half an hour.
As a professor in chemistry in VS University, Nellore, AP for an year, and presently he is the CEO of GII, which is called the Gemological Institute of India, where the diamonds and artificial and real diamonds will be tested for its defects and other things. It's in Mumbai, and he did his postdoctoral work in the University of Mainz, Germany, and worked in International Atomic Energy Agency, Vienna, during 1999 and 2000 as a technical officer. And his areas of research interests are nuclear fission, nuclear reactions, nuclear analytical techniques, non-destructive assay methods, electroanalytical chemistry, environmental science, and spectroscopic studies of diamonds and gemstones. This would be a very interesting lecture for all of you, those who are fond of diamonds and gemstones. And he has about 750 publications in journal and symposia combined, co-authored 5 books, and edited more than 30 books and some compilations also. So I invite Dr. Reddy Garu to deliver the talk on luminescence spectroscopy for determining the depth profile of color centers in diamonds. Thank you, sir.
Just a minute.
Thank you, Dr. Harnath. Good afternoon to everybody. So far you have been, do I need a mic? So far you have been listening. So far you have been listening to soft materials. Started with solutions, from their soft materials. Now I am talking about the hard materials, rather hardest diamonds. This is about how to use luminescence spectroscopy and spectrometry. Basically, after characterizing, that is spectroscopic aspect, then it is we are measuring, so it is spectrometry of the depth profiles of the color centers. So I will explain you a few details, and it is a focused topic, only on one topic. And if you get any doubts, whether it is in this or any chemistry, I am leaving my email. It's my habit, all the children, for students particularly. If you get a doubt, you write to me. Every Saturday, I sit for 4 to 6 hours to educate myself by clearing your doubts. Any question you please ask. There is no question about, there is no issue, right? It makes me to see my books and library, etc., etc. Yeah, regarding the topic, this is the plan I will explain in the next slide. Yeah, if you have problem, I will do. No? Okay. So I will talk about introduction because this is fairly new subject, and of course, ladies and girls will be knowing it. And the diamond type, that's an important aspect for this talk. And then color enhancement, because there is a fancy, there is an approach to improve the color of the diamonds by different treatments. Then I will give a overview. I will switch over to the main topic of how to measure the color centers inside the diamond. Then I will talk about just a few minutes how we characterize gemological by gemological methods and spectral methods. And Raman spectrometer, I don't know how many of you know, students particularly, otherwise happily I would have given a lecture on that, because morning onwards I am seeing lectures on different things also. I would have given a lecture on that, and I will explain it just in one slide. Then how we analyzed the data and evolved a new methodology I will explain. Then I will talk about some salient features. After that, a rare case we have seen. About that, I will explain you how we utilize this to get the genesis of that particular gemstone. And I will give just 1 or 2 slides on a case study of a color stone using the Raman spectrometer. And of course I summarize. It is planned for 25 minutes, but in 3 modules. Whenever you get bored or whenever chairman gets bored, I will stop. No issue about it. And while going through, if you get a doubt, without a hesitation, you raise your hand and ask. Or at the end of the lecture or over tea time, anytime, I will be happy if it is an interactive lecture rather than just delivering and going home. Since morning only one person is interacting, that is myself. Nobody else is talking. The conference is the one, everybody should learn something. Or everybody should share, because collective learning is the easier way to assimilate knowledge. Alright, next one please. Yeah, before I go into the topic, I want to say that GII stands for Gemological Institute of India, as Dr. Harinath has told. Oh, I forgot to thank Harinath for giving an introduction of myself. And in GII what we do is, it's a small institute of 60 people. We do testing of the diamonds, gems and studded jewelry. We charge them. But to develop the methods, we do R&D. So this is all the thing what we are doing there. We have expertise in. Can you read in the last people, last bench people? Can you read this? Is it readable? Doubtful. Can we expand a bit? Okay.
Focusing problem.
Okay.
Let them come and sit.
We can ask them to sit in.
Yeah. Why don't you please come forward? No? Okay. So we have expertise in grading, expertise in gemology, spectroscopic spelling mistake, equipment and analytical equipment, and we carry out R&D. And GII, because of its research and development, DST, Government of India has recognized it as a Scientific Industrial Research Organization, CIRO. That is supposed to be a prestigious thing. Okay, now we will come to the topic. So, one thing you have to see in this entire slide, what I have written is about the work we have done, because if there is a tiny defect for human eye, it is not visible. A tiny defect in a diamond is not. Any question please? It is not visible to human eye. However, there are instruments which will give you a clue. But this photoluminescence spectrometry is a wonderful thing which will go up to 10 power minus 12 if you use a laser as the source to excite. How many of you heard about a Raman spectrometer? Good, very good. No, not you people. Okay. You all know that you need a source. How many of you understand Raman effect? Poor fellow Indian got a Nobel Prize. Anybody knows? Anyhow, now I will not take into the interaction mode for that. So there, it's a wonderful technique to understand the interior structure of various materials, even the hidden structures. And both in scattering mode as well as in PL mode. It can be, you can work in scattering mode as well as PL mode. Essentially, not essentially, Sir C.V. Raman got Nobel Prize only for scattering mode, explanation of scattering mode, whereas PL mode, it is more useful now because its sensitivity is 10 power minus 12 molar, which is very high, right? So,
Defects, if you find out a small defect in diamond, will it decrease the price?
Is the question, if you find a defect, if it is visible, they are visible. This sort of thing will not matter. If it is visible, the price come down by 50%. And how much you don't ask? A good quality diamond per carat, 200 milligrams costs about 6 lakhs. Now we are working on it is confiscated. Also, and wonderful materials are there. So that is the thing.
Is it possible to rectify the defect in the...
No. Absolutely no. Absolutely no. Is it vibration of the instrument, this one, or vibration of myself? I am not, because I don't even drink anything. I just took a chicky, a groundnut. Okay, fine. So, what is that you asked?
Is it possible to rectify the defect?
No. Absolutely no. Absolutely no. So we are very helpful to price the diamonds, but we don't price. And by the way, I am happy to tell you, Lord Venkateswara's all diamonds and gemstones, we grade and test once in 6 months. So we come there. Only COVID time it stopped. Only last month I was called to give a protocol. I gave. So we will be coming once in 6 months.
They cause any...
They collect and ask us. There are certain areas where you won't question. Like you believe God, you go there. Like here also they call us, we do. I really don't know why it is so. Supreme Court stricture. Yeah. All right. So we have a confocal Raman microscope. We use that to measure the PL spectrum. Of course, for other work we use the in scattering mode also, but for this work. Okay. Well, this is the line I want you to note that sensitivity is very high. Very high means number should be low. Please remember. Even a small quantity will be measured. Okay. Okay. Fine. This is the thing what I wrote. Depth profiling of defects in diamonds is an art as well as science. And I have utilized, as introduced by Dr. Harnath, I was a hardcore nuclear chemist and nuclear physicist. And I never knew spectroscopy in the sense except that for the exams. So neither solid state. I was later last 10 years as analytical chemist, I was a liquid state spectroscopist. But all the instruments I used. Since there was a necessity, they invited, so I joined. Now I am dabbling with this. Now I am finding it is also interesting. Interesting. So just learning something. Life is always to learn, right? Okay. Yeah. We have contributed a methodology, a deconvolution method, which seniors will understand. I will try to tell. And this is the contribution. For sure it will come as 1 or 2 publications. Yeah. Next one. Yeah. This morning I was asking, who is that? Niraja and Anju and Anand. What is the meaning of band? Right? So they just got a bit confused. Anyhow, I will not go into a definition. This picture I have taken to show that what you know already is diamond is an insulator with a 5.47 EV band gap. But if there is an impurity present in it, it will reduce the band gap. Once you reduce the band gap, then the energy will be reduced. And if you illuminate with the light, then the corresponding absorption or reflection or emission will correspond to color. So diamond gets colored, its value goes down. Right? There are some special diamonds where value also will increase. I will tell that. Similarly, if an acceptor level is there, same situation. And remember, if you remember your periodic table, happens to be my postdoctoral work, extension of periodic table elements 104, 105, 106, it's very dear to me. I might have given 50 lectures on that. So, you have carbon at a 4th group, right? Carbon has 6 electrons, 4th group. Its right neighbor is nitrogen, left neighbor is boron. In diamond exists as a crystalline substance with a sp3 bonding. So, totally all the electrons are utilized. Therefore, it is non-conductor. Okay. Now, if a carbon is replaced by nitrogen, which has 5 bonding electrons, what will happen? 1 electron is loitering, freely available. So it moves around, it won't keep quiet. This example is not this is for corundum. So that electron will makes it a conductor. More than that, it will reduce the band gap and it will provide the color. If the concentration is less than 10 power minus 9 molar, then you won't see it. But instrument will see it. Similarly, boron, to the left side of the carbon lattice, carbon in the periodic table with 3 electrons. So it will create a hole, lack of electron. It will also behave like a conductor. That is the thing what we call a P type and N type. If it is extra electron which is ready to give an electron, you call
N-type, other one is P-type. Anyhow, now similar thing is true for the color stones. They are all either alumina network crystals or beryl. Now remember, if you see, diamond is the hardest one, close packed one. Can you believe that it has empty space? How many know it? Diamond, which is close packed one, crystalline substance, typically cubic structure, but it has 66% of vacancy, volume, by volume wise. Do you understand the meaning of it? You take an example of a glass, in that you put the marbles, put the water and measure, 66% at least will be the water volume. What does it mean? It has the spaces in between where atoms of different size or ions more rightly can enter. The moment they enter, that is impurity or imperfection, right? So that is the thing, clue we get to utilize to measure its presence. Okay? Right. Yeah. Now one example. Ruby is alumina, useless color, that is dirty white. But if you have 0.1 to 1% of chromium 3 present in it, it is a wonderful ruby. That provides the color. And chromium, all of you know, is transition metal. D orbital splits such that that gap is about 2.3 eV, ekdam red color. We will not spend time in this. Now we will proceed to the topic. Yeah. So before going to that, since I said GAA work, there are 4 types of diamond: nitrogen's presence, nitrogen's absence. The nitrogen presence you call type 1 diamond, 99% of diamonds of that type. Type 2 is no nitrogen. It can be with boron, without boron. Then you call all this one. And type 2A is the thing where the problem started. All the synthetic diamonds are placed there. You can recreate the production of the diamonds in the lab. There are 2 methods. By recreating the earth conditions, HPHT. Otherwise, this is CVD, chemical vapor deposition. Now it is very popular. People started producing as huge as 1 to 5 carat diamonds. You and me cannot make out. Unless I take it to my instrument, we cannot make out. And they are beautiful. And at 20 to 30% rate. So for us it makes no difference, we can purchase. This is the problem, but we have to differentiate. Okay. Next one please. So there are diamonds, if nitrogen is present a bit more than required, about 0.1%, those diamonds get a color. That is mainly yellow tint, yellow color. Suppose we can push it to red color or orange color, pink color, then their value will go up. So people are trying to change the color. Here, my earlier experience I have utilized nuclear science. Whenever a material is exposed to ionizing radiation, physics people should know in BSc first year, whenever a material is exposed to ionizing radiation like alpha, beta, gamma, it will either cause ionization or excitation or radical formation. How many of you know? Alright. When it moves through the matter, think about alpha. Alpha is a positively charged particle. When it goes through the matter, it will interact coulombically with electron. Then electron will get some energy from it. So its energy will be in the kinetic form. It cannot stay in the same orbit. It will go to next orbit. What do you call that? Excitation. Suppose its energy, whatever it gained, is more than the binding energy, it comes out, what you call ionization. Suppose it happens at the bond, it will break into 2, that is a radical formation, right? So this is the effect. This is taken advantage in diamond industry or the color stones. If a diamond is exposed to controlled radiation, then it can cause the color enhancement. Inferior diamonds nowadays, people try to expose to electron beam and change the color and gain money. Okay, this is one aspect. Now, how to know whether it is exposed to artificial radiation or something else? What is that something else? In the earth, when diamonds are formed,
If they come in contact with uranium material, a series of metals, in 12th class now, right? 4n series, 4n plus 1 series, then those both uranium and progeny, they emit alpha particles, beta and gamma. If they are in contact, then alpha causes ionization that will give the color, generally blue or green. Generally. So how to know? You know that alpha range is very small, whereas beta can penetrate deep. So here the role of instrumentation, our method comes into picture. We do on routine testing of colored diamonds to find out whether it is artificially irradiated or natural. Natural means its value will be very high. Artificial means its value will be low.
If a common man went to the shop,
You cannot make out.
you cannot make it.
Impossible.
So it's a cheating.
That is the precise thing, business. The greed for money, a bit more money. So people are innovative. So you have to accept it. There is no option. Only thing, you and me are not there. If we are there, we would have been a bit better because we have better IQ. We would have spoiled further. And don't mind. So that is the basic idea. And that is the point where we certify. Yes, please.
Sir, how the color define the purity of the diamond? As you are saying that like if it is pure red in color, then its rate is increased. So it means it is pure. That's why its rate is increasing.
That's a very good question. She is asking, how do you define the purity? How do you define purity, by the way? You have passed 12th class, no? How do you define purity? Let me take 1 minute, but I will cut my talk. There is no issue. Yes? How do you define purity? Yes? Anybody? Quickly. How do you find out the contamination? How do you define the contamination? Just 1 second. How do you define the contamination? Huh? Suppose by mistake I keep this in my pocket. It should be on the table, na? Finding a material in the wrong place. Right? What is a pollutant? If it does harm, then only pollution. Otherwise, nothing to worry. I will keep it back. Purity means any molecule that doesn't belong to the system. Presence of any molecule or ion or atom in a matrix which doesn't belong to those molecules. Iron rod is pure because it contains iron all the way. Suppose, right? Gold is pure if it doesn't go to the goldsmith, right? So diamond is pure. Diamond is pure as long as it contains carbon, right? Absolutely no issue. But the color is because of the effect. Consequence to an effort. It's not, nothing is added there. Followed? You still cannot call it impure. Okay. But did I say purity? I didn't say anything about purity so far.
Like you told us, if it is red in color, then the cost is more.
The bright color?
No, bright color costs more because there's a fancy. That's why they are called fancy diamonds. It's a shauk. Hindi lo shauk antam. English lo Japali. That is just your liking. Right? That is the thing, right? Okay. Good. At least one question is there. There are lots of questions. Good. So this I explained already. If this radiation interacts in the diamond matrix, it will cause ionization and it produces the color. And this color can be identified as a luminescent peak. That's called GR1, great radiation or grand radiation, GR1 center. And that is the thing we can tag and find out as a function of depth. If you have provision to measure, which I will show we have, then if it is deeper, then it is artificial. If it is on the surface, shallow, then it is natural radiation. That is the thing what we have carried out. On an average, we test about something like 40-50 stones daily. Whenever it is interesting, I go with the depth profile. Otherwise, just characterize and leave it there. So some 6 stones I am presenting here in the last about 6 months. We got some good stones, interesting stones and colored stones, so we carried out. Okay, now irradiated diamonds show GR1 peak that corresponds to 741 nanometers in PL spectrum. And natural diamonds might also get radiation effect, which I explained in the earth, right? And naturally irradiated diamonds have non-uniform color. Wherever they are in contact, there only it will cause the color. And by the way, the coloration was done by who is the gentleman? X-ray discoverer. He did that. Röntgen has done just for Taman. Becquerel has done, later published also. Whereas Raman spectrum was done by none other. Diamond spectrum was done by none other than Raman. First, he has done with a small Raman spectrometer. And depth profile was carried out by us by tagging GR1 peak, which I will share with you the data. Now, of course, I can go faster. Okay.
So that is the one way to identify natural and artificial.
There are many methods. There are many methods.
For a common man to identify if the non-uniform color is
This
there,
is a question which I will take 2 minutes and answer. How to know a diamond is natural or synthetic? You need not do this. This is for deeper understanding. Whereas we have developed a machine, Dr. Shastri was responsible, that based on luminescence and luminescence in the fluorescence mode and phosphorescence mode. Because diamonds, after absorbing the UV light, when it is exposed to UV light, it will give the blue fluorescence 85 out of 100. There are some stones which we refuse, inert we call. Whereas synthetic stones give red phosphorescence. Phosphorescence in 2-3 colors. So, fluorescence, we capture a photograph. After a gap of 10 seconds, we capture the phosphorescence. We cover about 95% of the diamonds. We give a certificate. In fact, we have put 2 kiosks. You can come and you test your diamonds for a small charge. That is for we assist. So, based on fluorescence and phosphorescence, using the PL measurement, you can decide yourself, and the machines, we have sold 400 all over India. Our machines are there. We call it as quick check. Quick check. So based on the PL measurement. So you can find out yourself as a first level. That is if there is a mix-up. But what we are talking, it is not the mix-up. It is a bit of more than that. Cheating. Right? And that too particularly when you have the solitors of 1 carat and above, this is a requirement. Whatever I told, that quick check, most of the times you use about 0.1 carat and down. In one go you finish it off. So, as I told you, size if it increases, the rate goes exponentially high. So therefore detailed studies are required.
Will they certify this?
We certify.
So, if we ask, suppose we are going to buy certain can we ask them to
show the certificate? There will be certificate. Good standard shops, they keep the certificates. Most of the times you see GIA certificate or GIA. There is a competitor from America. Well, in the export, they have an upper hand. In the local markets, we have upper hand.
So I have a small.
Please.
Saying that diamond now, how you are absorbing, where you will observe, because the SP hybridization and
Observation.
Yeah.
Observation. Crystallography, how much you know?
Yeah, that's what I'm asking.
Crystallography, how much
you can explain that where you can detect by instrument.
See, he has a very good question. SP3 hybridization means there is not big scope for
simple UV
any IR activity.
Yeah.
Raman spectrometer and IR are complementary. You need some centers to be formed beyond electronic transitions. That is vibration states or rotation states. And imagine this is closely packed diamond, and this man turned to talk to this girl. You will not do that, right? The next man, curiosity will bend here. Next man bends here. After some time, he said, "Get lost." You will go back, right? Entire network will start vibrating, right? Because when they come closer, nuclear repulsion, both Coulombic, electronic as well as nuclear, and over and above, and more importantly, it will create the sound waves, phonons. Like energy waves are photons. Phonons will be absorbed. Again, identical to energy diagram. So, for vibrational spectroscopy, phonon absorption as well as this sort of variety, I mean, you will be surprised to know it gives a rich absorption spectroscopy. Color centers is later. and minority effects. Absolutely perfectly pure diamond also gives the spectrum because of one phonon absorption or two phonon absorptions. Clear? Or confusing?
But still you have to say that luminescence also. How you are going to confirm the luminescence?
Luminescence is very simple. The moment you talk about vibration in the high energy region is in the color region. So you are getting it. There is no doubt about it. I presume that everybody knows here.
Sigma bond, that's why you are talking. It's not, there is no pi, the one is sigma.
You please come out of the bonds. You come out of the bonds. You remember this girl only. You come out of the bond, right?
You are talking about phonons.
Not only phonons. The movement of yourself is creating a vibration. This vibration can be one center, can be one atom, others can be infinity. So mass asymmetry is there. See, you need a charge asymmetry or mass asymmetry. Mass asymmetry is created in the vibration. Imagine about this class vibrating in this direction. Definitely asymmetry, right?
So you were talking about lattice modes.
Lattice modes. Network. Diamond is a rich absorption spectrum. It gives a rich absorption spectroscopy. And if at all there are small imperfections, then it is maja. You get a lot of peaks. Huh? If you are clear, is fine. Otherwise, your dinner I will spoil. We'll talk. Okay. 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 We have carried out systematic studies only on 6 diamonds because lots of have come, but this is enough to get him to develop a methodology, and of which 5 are natural diamonds. In the first phase with IR itself, you can find out, or since it is color, our machine will not work on that because we are photographing only color. So we go with IR, and of the 5 natural diamonds, we found 2 are natural and 3 are treated with the electron. We concluded that. But the 6th one is a very interesting thing. A CVD, somebody tried to make it as, sell it as natural colored one. That we found out. A very interesting observation. Next one, please. You please tell when I have to stop. There is no issue. Yeah. So, IR and UV visible measurements we have used for determining the type of diamonds. I will not spend time here. And PL spectra using the confocal Raman microscope. We have a microscope with 6 lasers, another one with 3 lasers, and 2 more with 1 laser, which are portable we have. For any material testing lab, a Raman microscope is Raman spectrometry is a gift, boon. Okay. Then the last one, you see, the beauty of Raman spectrometry is that it gives a diamond line which can be used as a this is our contribution now, which can be used as a reference for the effective mass of the diamond probed by the laser, because solid angle etc. we need not calculate. Extremely useful for internal normalization. It so happened in my thesis, in the nuclear reactions, I have used the internal normalization concept, which is accepted by journals. I thought I will use this here. It became very useful. Next one. The thesis was in 80. Right? Okay. Now what we have done is, under diamond view, there is a machine, diamond view, where we expose to UV radiation, where we could get the structures. The structures suggested that they are natural diamonds. This one is natural. The other zigzag structure, see, this structure clearly tells it is natural, whereas that one is treated. Yeah, next. I will go slightly faster. These are the FTIR spectra, where we see a variety of absorption peaks. All are characterized. I will not spend time on that. The moment you see this plated peak at 1362, one can say simply it has full of nitrogen. Nitrogen, when I say full, but less than a nanogram, nanogram per gram, right? Okay. Next, please. So, here UV absorption spectra we have seen. In the case of untreated one, the signal which is expected to GR1, which also gives here signal, it is not seen below detection limit, therefore it is natural, whereas in the other case, we got a huge peak which corresponds to, which from that we can tell it is already treated. But to identify further, to characterize, we have carried out the studies. Yes, please. Now, this is a photograph of our 6 laser Raman spectrometer, and most of you should know the path for the probing signal and measuring signal of emitted light are same. This is the beauty, means you send a laser through this onto the diamond, and when it interacts with the defects in the diamond or color centers, it produces the luminescence peaks, which are when emitted, they follow the same path. But here we use we use instrumental people. Mirrors are arranged such that this will be rejected and we get only PL peaks. And of course we have a CCD detector where we measure the things. Next one please. Yeah, these are the technical details of different lasers. The beauty of the laser is signal strength you can increase as you like, so that you get enough measurable signal. Signal strength, I mean probe strength. Yeah, next one.
Power on.
Wait, probe, I said. Come back to that one. I don't remember the number. Yeah.
There's a wavelength. Power.
This power is about somewhere around 0.1 watt or so. I will let you know. It's very high compared, but I somehow did not write. Yeah. Yeah. So I have used two lasers in the beginning, 405 and another 600 and odd, but I realized those spectra is rich here, but for some convenience I used the other laser. The next one please, because yeah, this is a PL spectrum with 633 nanometer laser, where my measuring signal, main signal is pretty close to this. You all know the meaning of this. So the probability for getting GR1 by 633 is more, it is more compared to the 405 nanometer laser. For comparison I have given for the same diamond. So for further studies I used this. Yeah. Yeah, this is the typical diamond picture. Cut diamond, round RBC cut diamond, and normally what we do is we keep the diamond on the platform in this position with some stick, and then we probe from here, and PLs whichever come we measure. Only thing is the solid angle is impossible to measure, you have to compute. I used internal normalization and avoided that also. Yeah, next one please. So this is the typical depth profile I have given for two. This is the untreated one. If you see after 2-3 depths about 10 micrometers, there is no response for GR1. Whereas here it continued throughout the depth we probed. That means the synthetic diamond was treated with a long range radiation so that volumetrically you have got the color. Yeah. So PL spectra were analyzed using Origin software to obtain the peak area and centroid counts as well as peak area, and we used both the things and concluded that both are good parameters to use. For further studies we took only peak counts. It can happen only if the peak shape is absolute Gaussian. Yeah. Yeah, this is same thing whatever I told I showed. They are parallel lines. So for further work we used only the centroid counts. Yeah. Yeah. Then all the 5 diamonds we have plotted the profile. You see the natural diamonds only surface is about 10 micrometers, whereas for other 3 synthetic diamonds this is continuously having the color. So that tells that this is treated with a long range radiation. Yeah. Yeah. Compared to diamond Raman, what is the importance of this particular plot is, we have plotted a diamond Raman line which is only directly dependent on the diamond weight. Surely, close. And whereas the GR1 depends on the treatment, but they are simply parallel lines. So once we normalize, efficiency part will be over. That is taken as a constant. So the next one is the complete one. This after normalization, we got clearly as a function of depth, color is uniform. Whereas for natural diamonds, it is just at the surface. So this is the way we can characterize and understand. So contribution from this is, besides testing, we developed a method, a methodology. That is the thing what we have done. The next one quickly I will do in 5 minutes for sure. So what happened is, the 6th diamond why I took here is, it's a CVD diamond. And I don't know how many of you know CVD diamond. What is done is, you keep a wafer, diamond wafer, either natural or synthetic, or simply silicon wafer, again periodic table. Just below carbon you have silicon. So they have similar properties. A silicon wafer people keep and grow the diamond. Afterwards, silicon wafer will be etched out, thin wafer. So then it will appear as if it is natural. So what we have seen here is which normal instruments cannot identify. So minute amounts of silicon could be left and its detection is beyond the capabilities of most of the instruments. Next one please. What we have done is, when we were carrying out these studies, depth profile, it was showing a color center which is not supposed to be there, but after some time, after some depth, it has stopped showing the GR1 signal. What does it mean? The next one please. So this way I have analyzed same depth profile whatever we have done. So as far as the GR1 is concerned, only at the surface. That means they have succeeded in removing the surface material, silicon on surface. But while CVD is formed in, diamond is formed in CVD method, some silicon atoms migrated into the bulk of the diamond. So when it was exposed to electron beam, those silicons have created a SiV minus centers. So SiV minus center, which is at 737, when we plotted, initially it is nothing, later it started increasing, after some time it stopped. That means they have used silicon, etched out, but still some silicon atoms were, they diffused into the bulk of the diamond. But for human eye, for normal instruments, it was in fact certified as a CVD, an absolute high quality CVD. We also endorsed, but we wrote, still some silicon atoms are there. So, okay. So I thought this I will tell, but in this process, we developed a spectral deconvolution method, which was available, we adopted and demonstrated. Probably this also can be sent as a technical note. With that, my presentation is over. Next one, summary. This I thought lost. Okay. We can use Raman spectrometry in PL mode and both the modes to characterize the color stones. We use regularly, but more in scattering mode. I'll just give an example in the next one. Next. Yeah. See, this is a case study we have carried out where there were zircon inclusions in pink sapphires, and we could find out them because zircon structure is different than corundum. In scattering, clearly they could be seen. They are actually zircon inclusions are there. Then heat treatment was given. Heat treatment is one of the things for annealing to get the peaks uniformly. So by this we could find out and certify that yes, there are not only zircon inclusions, they are heat treated. But this PL area, probably after my going there, I will look into that. This also will give the useful information. With that, my talk is over. You see the next summary. What we have done is we have characterized and developed a methodology for finding out the depth. In the process, we also developed a methodology to deconvolute the different spectra using origin software but adopted. And PL with Raman laser is extremely useful for detection of minute levels of impurities. That is the thing what I want to say. This time it is impurity, silicon presence. Whereas when you have a color center, it is not impurity. It is in part of the material got into ionic form. Okay. Thank you very much. After initial questions, I think people have become silent. In any case, thank you very much.
So who was the manufacturers of synthetic diamonds in India?
Surat is a big hub, Jaipur is a big hub. Lots of people are there. At least there was a conference last year. There were about 400, I have a list of 400 people, more than that, they are there. They all send the diamonds for test, not all. Some people send diamonds for testing. Now we are requested to open a branch in Surat so that they can reach there. So our credibility is pretty good in that.
So
there are many, yeah.
I have seen one paper, there is a 1332 wave number.
1332?
Yeah.
Centimeter inverse.
Yeah. So that
characteristic.
Yeah, it's big. That means that is not the lattice mode. That is not the lattice.
No, that is a sheer vibration.
Yes.
For that there is such diamonds have some other criteria to have. 1332 is characteristic. Yeah. Thank you very much. Yes, please.
Sir, you choose that the laser wavelength. So on what basis you are choosing the...
Exactly proximity to the signal what you want to get. I want to study 741. The closest laser among them I have is 683. That is the thing I compared, 405 and 603. Where GR1 at least was increased by about 100 times the intensity. That is the criteria. Good question. Always closer. Finally, when you talk about PL emission or vibration, spectroscopy, it is resonance is the important thing. If you talk about Raman, resonance is not required. Okay? Since we are using in PL mode, if you are closer to it, if it is resonance, ideal. Otherwise, at least if you are closer to it, that will be better signal. Thank you.
Thank you very much, sir, for a wonderful lecture. And today afternoon is really started with your talk. Generally after lunch, it is very tough to listen find the people also. Thank you very much, sir.
Actually, I am not boasting myself. Often I tell in our workshops, give me a lecture after lunch, I will make sure that nobody will sleep. So I am very happy even here. I am a baby in the subject. I am not an expert. So still I could keep you awake and hear what is written. Thank you.
At least we have to inform to Professor Murthy to arrange always a luminescence conference after lunch only. On the behalf of organizing committee, a small token of honor.
A token is a token. There is nothing like small.